Hi everyone, my name is Qindan Zhu. I'm right now a postdoc at Department of Earth, Atmospheric, and Planetary Science at MIT. My talk today is to utilize a machine learning model to estimate the OH trends over North American cities. The OH radical is the most influential oxidant in the daytime chemistry for different scales. On a global scale, it determines the lifetime of greenhouse gases, but over urban areas, it affects the local pollutants as it initiates the oxidation and removals of both NOx, VOC, and many other pollutants that are mostly emitted by anthropogenic sources. So far, the local pollution, especially the ozone exceedance in the summer, is still a remaining issue for North American cities. The map from LA colors the counties designated as ozone non-attainment area, and these counties are located either at the urban center or in the vicinity. There has been multi-decadal efforts to control ozone pollution with significant NOx emission reduction, since NOx is one of the primary ozone precursor. However, the reduction of NOx emission does not directly link to a simultaneous ozone reduction. This schematic illustrates the ozone production rates as a function of NOx. If the urban regions is currently in the NOx suppressed region, further reduction of the NOx will actually lead to a simultaneous enhancement of the ozone production rate. Whereas in the NOx limited region, the ozone production rate shows the opposite relationship with NOx. If the urban areas is currently in this region, NOx emission reduction is more efficient in eliminating the ozone pollution. From the chemical perspective, OH as a function of NOx closely tracks the relationship between ozone production rate versus NOx. That said, if long-term OH trends are available, we can actually utilize the relationship between OH and NOx as the implication of the chemical regions at the interannual timescale, and these will provide a scientific evidence to help the policymakers to issue the most effective strategy of controlling ozone pollution. So the question is now anchored to how can we constrain the urban OH at this long-term timescale, while the measurements of OH are quite sparse both in time and space. In my study, I propose a machine learning approach to be the solution of this question. Specifically, I will train a machine learning model based on the outputs from the chemical transport model. And these chemical transport models are very computationally expensive, and it includes all the physical and chemical details that we can think of in the atmospheric chemistry, and run this model to generate the 3D prediction. And once this machine learning model is trained, I can get the machine learning predictions based on the inputs constructed from the satellite observation records. The selection of the input feature for this machine learning model are based on our understanding of the OH chemistry. For instance, the figure on the right just shows a very simplified schematic of the OH chemistry, while geosynchronity and water vapor are two major components that affect the ozone production rate through the ozone photolysis. We have the NO2 column or NO2 vertical condensate VCD as a proxy of NOx, and NOx involves in the Hawkes cycle as well as the same pathway of the OH by forming the nitric acid. For formaldehyde condensate, we have it as a proxy of VOCs that involves in the Hawkes cycle as well. From the figure on the left, I'm showing the performance of this machine learning model by incrementally adding the input features. And we could see that while we are adding these two column input features, namely N2 column and formaldehyde column, we see the largest improvement of this machine learning performance. And the finalized machine learning model with these 6 input features yields a correlation coefficients of 0.76 and a root square error of 2.1 times 10 to the 6 molecule per cubic centimeter by comparing the machine learning model predictions against the OH directly from the Wolfram simulations, demonstrating that this machine learning model is a good representation of the OH chemistry from this computationally expensive chemical transport model. I then were able to construct the features from the observations. For the features listed at the bottom, I still use the outputs from my Wolfram simulations because in my model setup, water vapor, temperature, and pressure from the observations are not every 3 hours, so the model simulations should closely track the observations. For the remaining 2 column features, I can get it from the satellite observations. Specifically, I will use the Bayer retrieval product to get the O2 condensity and the QE4 ECV product together for Manhattan condensity. Both observations are regraded at 12 km times 12 km to match the native resolution of WorldCam simulations. Once these input features are constructed, I can feed it into this machine learning model to yield the OH prediction that are based on the observation constraints. Starting from these slides, I will just show the results based on these OH predictions from this machine learning model. First of all, I want to show the OH trends over these different regions. We are noting that there is a slight decrease of the OH trends. We notice that there is a slight decrease of the OH trends if we average all the OH predictions over these 49 North American cities, and the decrease is about 6% between 2005 to 2014. However, on top of that, what's more interesting is we note a very large seasonal-wise variation. For LA region, we show a significant increase by up to 10% of OH between 2005 to 2014, whereas in Bakersfield, a city that's not very far from LA, shows the opposite pattern featuring a larger decrease of the OH comparing to the city average scenario. The map on the right shows the relative difference of the OH between 2005 to 2014 among these 49 North American cities, and the bottom right shows a corresponding distribution. We note that a small amount of cities present the increase of the OH, including LA and New Orleans, while the remaining cities shows a decrease, and the overall relative changes of the OH ranges from -15 to about 10%. So what can we get from the OH trends predicted from the machine learning model? As I said in my introduction slides, we can utilize them to prop the chemical reagents. First figure is showing an example from LA, and I'm showing the density plot of the OH predictions versus O2 condensity from satellite observations over LA regions in both 2005 and 2014. We could see that O2 condensity decreased substantially, while the OH abundance in 2014 stayed at a peak range of OH back in 2005. To quantitatively describe the changes, I calculate the slope from a linear feed of OH versus O2 condensity and define the slope as the OH versus O2 vertical condensity gradient. This gradient can map to these observations to the schematic that I showed in the earlier slides. For instance, LA in particular shows a switch of the gradient from negative to near zero, and mapping it to this schematic, it shows the transition from NOx suppressed region to NOx limited regions. I'm showing another cities like Denver. It presents a different patterns. The gradient stayed positive in both years and is larger in 2014. A mapping to the schematic shows that Denver was already in the NOx limited region in 2005, and it kept moving left due to further reduction of NOx. Okay, now we can extend this analysis of OH versus the gradient to these 49 North American cities in total. And I'd like to convince you that this gradient really serves as a great proxy for the chemical regions governing the corresponding urban circumstance. First of all, I'm showing the gradient in 2005 in these 49 North American cities. We see that the first 4 cities are characterized with the negative gradient, indicating that they were in the NOx suppressed region in 2005. There are a small group of cities on the right with a positive gradient, demonstrating that they were in the NOx limited region back in 2005, and a large amount of the cities were falling in the middle. However, if we switch it from 2005 to 2014, we see that the gradient experiences significant changes. In general, most of cities are seeing an increase in the gradient, but it's on different orders. For instance, the first group is showing a transitioning from a negative gradient to near zero or a positive gradient, indicating that they were transferring from the non-suppressed region to these transitional phases. The cities on the rightmost are still showing a positive gradient, but it's larger than it did in 2005, indicating that they were in the NOx limiting region, but it also comply with the behavior that with further reduction of NOx emission. The largest changes occurs for the middle group, and we found near 2/3 of the cities were in the transitioning. We found that 2/3 of the cities will complete the transition. The largest changes occurs for the middle group, and we found nearly 2/3 of the cities complete the transitioning between NOx suppressed region to NOx limiting region. And there are still 1/3 of the cities that were in the transition region. Comparing between 2005 to 2014, we can now conclude that in 2014, North American cities will either undergo the transitioning from NOx suppressed region or were already in the NOx limiting region. From the perspective of controlling ozone pollution, we can now conclude that for these cities, controlling the NOx emission in the future will be the most productive strategy in controlling ozone pollution. I'd like to bring back some of the key figures to wrap up my talk in these last slides. First of all, I trained a machine learning model based on the chemical transport model, and then use this model to predict the OH trends over 49 North American cities. Combined with the satellite observations, we can use the OH predictions versus the NO2 current density to prompt the shapes of the chemical regions that provides insights for the urban ozone pollution. That's all of my talk, and thanks for listening.